Hello, friends. This is a video about density and pressure. Let's begin. So density, I should say volumetric mass density is mass over volume. You can have any density, like linear mass density is mass over length. You can have energy density. You can have population density. Density is any quantity like mass, energy, people, etc., divided by a space, whether it's one-dimensional, two-dimensional, or three-dimensional. I guess we could even say a four-dimensional density. But obviously in the three-dimensional space, we're going to take a mass, right, and put it in a volume, V. Now I could make that mass tiny, and that makes the density go up, or I can make that mass bigger and make the volume bigger and have the density go down. So to have the density go down, I could either have what? I could have the mass go down or the volume go up. To have the density go up, I could have the mass go up or the volume go down. I could have it be small and massive. Think of the densest thing in the universe, a neutron star or a black hole. And the least dense things in the universe are huge. They're huge, huge and low mass, like a diffuse nebula or empty space, right? Where there's really little mass and it's enormous in volume. Cool. So yes, what is this little squiggle? This is the Greek letter rho. I don't remember why it's used. I'm going to look it up again. Is defined as mass over volume. Now the unit of rho, careful, what is mass? That's kilograms. What is volume? Well, volume is length times length times length, right? And length is meters, so it's meters cubed. So we want to be in kilograms per meters cubed. Cool. So the major thing here is we want to look at certain quantities and be able to convert their density or use that density in equations. So for instance, what if I have a cubic centimeter of water? What is its mass? What is its weight? Its weight, of course, is mg, right? But what is the value of it? So if I had, by the way, that's a milliliter. And so now we need some definitions. 1 cubic centimeter is defined to be a milliliter. So there are 1,000 cubic centimeters in a liter by definition. You can write 10 to the 3 if you like. Cubic centimeters make up a liter. So you can imagine a liter in your hand. Maybe do a cubic centimeter in your hand, like a little block. That's a cubic centimeter, a centimeter times a centimeter times a centimeter. Kind of like that. Right? 1,000 of those would fill a liter bottle. It's pretty extraordinary. You can think about that for a second. But then that's not a cubic meter yet. So how do I get to a cubic meter? Well, there's 100 centimeters in a meter. But to cube it, I need to cube the 100, right? Because to get to a cubic meter, I do 100 centimeters long times 100 centimeters tall times 100 centimeters deep. And I make it a big box. Maybe I can draw this one a little more parallel. This one got a little wonky. So 100 times 100 times 100, 100 cubed is 1,000,000 cubic centimeters in a cubic meter. Put that in your notes, put that in your notes, is 1 liter. 1,000 cubic centimeter, 1,000,000 cubic centimeters is a cubic meter. Do that with your hands, meter times meter times a meter. Now imagine that filled with water. How much mass in a cubic meter of water? A lot, right? It turns out the answer is 1,000 kilograms. And the reason is because 1 gram of water is defined as 1 cubic cent. Oh, sorry, 1 gram is defined as 1 cubic centimeter of water. This is actually the definition of a gram. I don't know if you knew that. It's kind of fun. This is the definition. This is where a gram comes from. Centimeters come from meters. Meters comes from the circumference of the earth originally. It's kind of fun. Grams comes from water. Seconds comes from the rotation of the earth. So earth and water are where we get our units from in the metric system. So if 1 gram is a cubic centimeter, that means there's, to have 1 kilogram, I multiply by 1,000, which means I multiply this times 1,000, but how many, if I have 1,000 cubic centimeters, what is that? Well, that's going to be a liter. A kilogram is a liter of water. And in class, I have already, or I will pass around a liter of water, and that is, you can feel it, that's a kilogram, 2.2 pounds. Now, pounds are technically weight. There is a imperial, this is called imperial system. It's called a slug, is the equivalent of a gram. It's really weird, nobody uses it, because this assumes we're on the earth. If you go to the moon, you have less weight, but you don't have less mass. So your kilograms doesn't change, but your pounds changes. Isn't that kind of crazy? So these are actually not equivalent. They're only equivalent on the earth. So we stick with the mass, and weight, of course, is in newtons in the metric system. Either way, if I have a kilogram, what is this? This is stuff. All right. This is space. So that's how much stuff fits in that space if you have water specifically. Obviously, I could make it more dense if I have a different material like metal or rock, or I can make it less dense like air, and I have a different density there too. So the two densities we need to know are water and air. We might deal with other ones, but really those are the two ones we really need to know. Might do like a granite stone at some point, but I'll give you that information. These I'm expecting you to have in your notes. 1,000 kilograms per cubic meter. Because wait, so it was like, wait, okay. A kilogram's a liter, but how many liters are in a cubic meter? So there's actually 1,000 liters in a cubic meter. So there's 1,000 cubic centimeters in a liter. 1,000 gets me to 1,000,000. So there's 1,000 liters in a cubic meter. So a kilogram is a liter. And so times 1,000 times 1,000, I get 1,000 kilograms equals 1 cubic meter of water. So the density of water is 1,000, know that. The density of air is 1.225. It's almost 1. So if you have a cubic meter, imagine a cubic meter right now, you can do it with your hands. And you held that in your hand. That would be 1.225 kilograms. It's like 3 pounds. 3 pounds of air in a cubic meter. Clearly a lot lighter, like almost 1,000 times less massive than water, less dense than water, given the same volume. Cool. So that's density, step one. Next, pressure. So pressure is defined as force over area, where the force is perpendicular to that surface. So I want to be careful. This is the definition, but this isn't the one we're always going to be using. Just this is force distribution. We already talked about this with the concept of the bulk modulus. That if I push on something with a force over an area, then the unit of it, this is just the definition of pressure, but not really the equation we're going to be using, is a Newton per square meter. It's force over an area, right? And if I concentrate that force over a smaller area, it increases the pressure, etc. And this is called a Pascal. I haven't introduced that yet, but now I am, and I'm expecting you guys to know that a Pascal is a Newton per square meter. It's a new unit. It's like a joule or a Newton. It's just one of our lists. It is a Newton per square meter. There it is. It's force distribution over an area. So immediately I want to go to hydrostatic pressure. The hydrostatic pressure is like, okay, say I have a jar of marbles. And I want to know what one of these marbles feels. Say I'm gonna, and each marble is a mass M, right? I want to find what's going on in this red one right here. Well, the whole point is think of hydrostatic pressure like normal forces from all sides. And that's a really big deal, all sides. So what is it feeling? It's feeling this arrow this way, not just down. It's feeling it at an angle. It's feeling this one from the side. It's feeling this one from this one. It's feeling this one from this one and this one from this one. And if you imagine these as water molecules, then a water molecule, a single water molecule, will be feeling almost infinite. You can think of it as infinite arrows, but it's not really infinite. It's just many, many arrows from all sides. That's hydrostatic pressure. Now, a question is going to be, are any of these bigger or smaller? Let's assume this thing is infinitely small, so there's not much depth to it. Turns out its height will matter. All right, that's a cool thing. But do you see how this is pushing back up? Right, it goes from all sides. So pressure pushes up and down when you're submerged in a fluid. So the pressure, hydrostatic pressure, is the weight of the fluid pushing on itself or an object in the fluid, a submerged object. I like that word, submerged. Cool. So that's the concept. So even if it's on the side here, the side is also pushing on it with a force F, action reaction, right? It's like normal forces from all sides. Weight of the fluid pushing on itself or a submerged object. That sound good? So let's derive it. So let's say, here's how we really want to derive it. We have like water or something. Yeah, it could be water or air or any fluid. So really, I don't want to draw, but I do want to draw the top. So there needs to be like a top. So let's say this is the top of the atmosphere. And this is air, and this is space. Just to remind us that this doesn't just have to be water. And here's Earth. And let's say I have a flat plate, because like I said, I don't want it to have any depth yet. This is a flat plate of area A. This is third dimensional. Right here. I'm trying to draw a flat plate or a piece of paper. Now it's not moving, so freeze time. It's not moving. So you don't want to think about it as moving up or down yet. That's step 3. We're at step 1. Step 1 is just, let's pause time. Let's look at the forces. Step 2 is we're going to include depth. Like I said, we're going to make it depth, and that's going to happen in the next class. And then step 3 is we're going to let it move. Then we're going to unfreeze time. That's step 1, 2, 3. And that's how I think it's best to understand this. So this is at a depth D. I draw like brackets, like I said I would. Starting green. And the density of air, of course, is density air. Great. So this is the depth, this is area A. So the whole point is the air is pushing down with a certain weight above the plate. Now I know it's pushing back up, but again, action reaction. If I stand here and there I am, right? And I stand on some bricks and I hold bricks on my head, then the bricks are pushing down with their weight. And then the bricks are also pushing up with me with a normal force that's going to counter their weight. But when I feel their weight, I'm actually feeling it as a normal force where I'm pushing back up, right? Imagine you're holding a bunch of bricks, you're pushing up with a normal force, it's pushing down with you with a normal force, right? That normal force is its weight, right? But then that's also transferring through your body to the other side. Because you're not falling, right? So I know I said we're not moving, but the point is there's something below you, right? Also, exerting a force on you. So even though the weight below, like the weight, how many bricks below doesn't matter. This normal force depends on what's above. I'm running out of room here. Hold on, I'm gonna do this right. This normal force depends on what is above. So the normal force up depends on what is above pushing down. I could be standing on one brick or a million bricks. This normal force will be the same because it's countering this weight of what's pushing down. So all that matters is this weight pushing down to determine the normal force that I feel and the normal force I feel from above and the normal force I feel from below. So the point is there's forces from above and below that depend entirely on the weight of what's pushing down. Because then you can imagine these molecules saying, oh, they're being pushed down also, and therefore they're pushing back up with a normal force. And they're supported by these molecules. And you might be kind of getting the picture here that the deeper I go, the bigger the normal force has to be to hold up all that weight. That's the point. So hydrostatic pressure, which we're going to refer to as P sub G, by the way, right? It depends on depth. Conceptually, that's why. Rewind that if that didn't make sense, right? Water or air or any fluid, the pressure that anything feels being submerged in a fluid is depending on depth, and it's the weight of the fluid pushing down on it from all sides. Because if you push down on something, the underneath pushes back up too. And even the sides push. Remember the jar of marbles? These are going to be pushing too, right? These are going to be pushing inward, right? You get normal forces from all sides. Go back to the jar of marbles, right? That even a downward force, right? A downward weight results in sideways normal forces sometimes. Like 3 balls pushing on each other, a triangle. Right? So a downward force sometimes results in sideways or diagonal or upward counter forces, and that's pressure. It's the response to the weight. It's not the weight itself. It's the normal force responding to the weight. So I should write that. It's the normal forces from all sides responding to the weight of the fluid. There we go. Got it. All right, so what's the formula? If I have a cross-sectional area A, and I have weight Fg at a depth D, right? Then the pressure is the force over the area. We're only going to use that as the initial definition, so I wouldn't memorize that equation. I would understand the concept that I was just outlining about normal force and depth and pushing from all sides and that whole thing. The response, think of it as like a normal force, right? Force over area, though, is the value of it. And for weight is density of the fluid times volume times G. And I realize I forgot something back here. And I said it, right? Which is, I said, what is the weight? Well, mass, where are we here? Mass is density times volume, because if I multiply by volume here, I get density times volume. So weight is mass times G, which is just density times volume times G. And the density is just whatever we're dealing with, the object or fluid. Now you want to know, are you dealing with the object or the fluid in any specific circumstance? But in general, weight is rho Vg, V is volume. G, of course, is 9.8. Right? Density, volume, we got it going on. So I have density of the fluid because the object doesn't matter. Like if I'm a turtle, a whale, a piece of paper, an airplane, a submarine, air molecule, anything, if I'm in the air, I'm feeling the weight of the air. I'm not feeling anything about myself. I'm holding up those bricks. If I'm in a sea of bricks, I'm holding up the bricks, right? So the fluid determines the pressure, not the object. And I distribute it over the area, but the volume, what is the volume? The volume, right? Think of it like the volume of a box, right? Here's the area. What is the volume? Well, the volume is area times height, but height is what? Height is depth in this specific circuit, in this specific drawing, right? So think of this volume cube or rectangular cube of air, volume of air, right? So the volume divided by the area is the depth. And we have it. That the pressure, the hydrostatic pressure, I write P sub G because it's caused by the weight. It's caused by gravity. Without any gravity, there would be no hydrostatic pressure, which is remarkable. Without any gravity, there's no hydrostatic pressure in space, unless you falsely apply another sort of pressure. There's no this is called hydrostatic pressure. It's a very specific form of pressure, which is caused by, if I'm just in a fluid and I go deeper, the water pushes on me more and eventually crushes me. That we're feeling an enormous amount of pressure from the air right now is the density of the fluid, FL is fluid, times the volume, times the depth, times G. So it depends on depth. Notice there's no properties of the object. And that deeper is more pressure. So right now, say this is space, and this is the air, and this is the earth. It's not like all of a sudden space happens. It's a gradual change. But the height of the atmosphere is around 100 kilometers. There's a name for it. Gosh, the Kármán line, there it is. I remember it. Which is like if you're above it, you're considered an astronaut, which is kind of cool. It's like you're in space. There's still some air out there. There's still molecules in space. It's not empty. Space is never empty. It's just really, really, really low density. The density up here is like 0.00000001 kilograms per cubic meter. The density of air down here is 1.225 kilograms per cubic meter. And the density near space, so density decreases, density drops as you go up. As altitude increases, density drops. That's that one. So on the surface of the Earth, though, right, we can take the average density. In fact, we could solve for it. We could take the average density of air, right? The average. This is a symbol. I think this is a symbol for average. I mean, that's absolute value. I'm being all foolish right now. Sometimes I've seen that. I think this is average. I'm trying to remember the mathematics. I know it's absolute value. I've seen that used in, anyway, doesn't matter. Doesn't matter. I think that's average. I'm like tricking my own brain right now. I'm confusing mathematical symbols. Average density of air, I'm going to pretend that that's the answer. Causes, even pushing up on your feet, because there's going to be a thin layer of air below your feet, causes the pressure of the air to push back up. I'm going to call it P air because it's PG for the air, and it's pushing on all sides. All those molecules are squeezing you like you're in a marble in a big marble tank of water. And that the pressure of the air is the average density of air times your depth times G. And if you multiply by the average density of air times 100 kilometers, but you need to be in meters, and you multiply by 9.8, you're going to get the answer. But really, we would use this to solve for the average density of air. And what we get is that the air pressure that we're all feeling right now, we just measure. You measure it with something called a barometer. You get 101,000 pascals, which is called an ATM. Now be careful, we're not going to use ATMs because we need to be in newtons and meters. So we have to use 101,000. And be careful, this is a K. So really, in MKS units, the hydrostatic pressure, atmospheric pressure, 1 ATM. I might trick you and write 1 ATM. I'm not trying to trick you, I'm trying to see, make sure you're paying attention. Pressure of the air is 101,000 pascals and newtons per square meter, or 1.01 times 10 to the 5. However you want to write it. Please know this. Please plug this number in for atmospheric pressure. If I say 2 ATMs, right? 2 ATMs, you're going to immediately convert to 202,000 pascals, et cetera, et cetera, et cetera. And there we go. That's what we got. Hydrostatic pressure and density. Feel the weight of the air. It's remarkable. It's actually a lot. 101,000 newtons per square meter. A lot. Why don't we feel it? It's because we're used to it. Our bodies push back with that same amount of force because we're in equilibrium. We're in hydrostatic equilibrium with our environment. We've evolved. If we go into outer space, you balloon like a balloon. You actually puff out because the internal forces of the fluids in your body, we're just a sack of salty fluid, right? Right? Push out and you actually balloon out in outer space. Suffocate. Stuck right. All the air will get pushed out of your lungs, pushes out, and you don't freeze. That's a tricky one. We'll get to that one in like a few weeks. There is no heat transfer in space, or it's very, very slow because there's very few molecules to do the heat transfer. Didn't mean to end that way, but either way, come back to the Earth. We're safe here, right? Holding up all that weight. You can marvel at it, feel it, imagine. Take a moment to visualize. All the way to the top of the atmosphere. Take a moment, feel it. Feel your heartbeat. That's really beautiful. See you in class.